No, okay, so I use the mic. So I'm going to use it. I'll try to at least. Okay, do you hear me? Well, okay, I try to speak normally and not to shout into the mic. Well, it's a pleasure to be here. I'm happy to thank the organizers. It's also a pleasure to be here and to dedicate this talk to Leonid, that I have known for some time now, though not as long as many of you. And it's a pleasure to see him in such a great shape, and the comforting thought that mathematical physics may be part of why he's in such great shape. So the title of my talk was The Low-Lying Spectrum of One-Dimensional Random Operators. I imagine to physicists not a very enthralling subject. So first I'll start with maybe with a motivation, right, that may be of more interest to physicists, which is interacting fermions. In a random background. So what I'll talk about first is the PhD thesis of a student of mine who is going to defend this thesis next week, actually next Friday in Paris 13. So his name is Nikolai Veniaminov. But before I come to the gist of his results, I want to describe a little bit the context, right? So what is the problem we're interested in? So, what we'll be working in the microcanonical ensemble. So we'll be looking for quantum Hamiltonians of the following type. So my basic Hilbert space will be L2 of some cube. Lambda is, let's say, think of it as a cube in RD. And of course, I'm interested in fermions, so I look at the antisymmetric functions with n particles. I don't think I'll give a name to this, no. Constructed from L2, right? And on this space, I look at the operator, which I call H, omega, U, and N. So N is the number of particles. And this is some free operator plus some interaction. And to make things simple, I suppose that the interaction are pairwise, and the results that, well, I consider most interesting we only have for this case anyway. And what is H0? So there is an omega which is betraying its random nature. And this is just, well, as you imagine, free particles. I forgot the lambda, actually. There is, of course, a lambda in here, but, well, let me forget about it. Let me forget about the lambda. And so this H omega will be your favorite operator, so random operator on lambda. On L2 lambda, right? So what we want to get is mathematical results, meaning theorems with proven estimates of all the terms or the remainder terms as well, right? So that we have hard estimates we can count on. So of course there will be a price to pay for that, right, which is, well, we'll have to look at the simple model. But before I go over to the simple model, oh yeah, one thing, of course, the n I'm interested in, that's important, is n, well, let's say rho times lambda, where rho is positive, and lambda, and of course then n, go to infinity. But I want to work at positive density. I don't want to work at zero density, okay? I consider many particles inside the. So I think this is the true quantum problem. And the question I'm interested in is, of course, what is the ground state energy? So this is ground state energy of H omega U N. And of course, also what is the ground state of the same operator? What can I say about the ground state of this operator? So, so first let me say something about the ground state energy. And actually the ground state energy, of course, I'll be considering the ground state energy per particle. So I look at, ground state per particle. So I just call epsilon, well, nu. This is the infimum of the spectrum. So my H omega, I didn't define precisely what it is, but think of it as, for example, Poisson model or Anderson model. And so it's lower semi-bounded, right? So also my interaction, I didn't say anything about them, but as you'll see, I make more precise assumptions later on. They'll be compactly supported and positive. So these are repulsive interactions. So obviously the infimum of the spectrum of H omega U exists and is finite. And you may look at the energy per particle, right? And well, the first thing is that what you hope for, so this depends on rho, of course. What you hope for is that this thing converges to some epsilon, what did I call it? Put the U here as I don't have any n anymore. Epsilon sub U of rho, right? When n goes to infinity. Of course, n of times rho lambda. So this is already a statement which is not completely trivial, right? You can show that actually, and this is part of the first part of the thesis, you can show that this thermodynamic limit exists, right? Well, exactly. So this depends. So if you take, for example, as I said, repulsive interactions here with compact support, then indeed you show that this limit exists almost surely. If you take non-compactly supported interactions, it's not a story. We only have L2 convergence up to now, right? So meaning that if you take the expectation of the difference of this minus this squared, take the expectation with respect to the random variable, this converges to 0, okay? So, but if you have that these are compactly supported, then you have almost sure LP convergence and AP. So that's the most interesting thing. And of course, what we are interested in is the behavior of epsilon u rho in rho and u. Right? That's the important thing. We'd like to understand how does this one grow when rho starts from 0, and how does it depend on the interactions u. Okay, so, and the second thing is, of course, well, we can define there is a ground state. It's not completely trivial that there is a unique ground state, that it is non-degenerate. So, and we'd like to understand whether this thing is localized, whatever this means. That's another question. Okay, so which is the second question I've put on the board? In which sense? What does this mean actually? And you'll soon see when I go over to the model what I mean. Why this? It's not obvious what localized means for this n-particle Hamiltonian, right? And so before doing that, let me just go over what happens when there is no interaction. Even though I'm sure that most of you already have seen this, maybe there are some people I nevertheless show something new to them because they never thought about it. But let's assume just for a second that U is 0, no interaction. So we have 3 fermions, right? Then it's well known that actually the ground state of this thing with U equals 0 is given by a Slater determinant. So what did I call it? Psi n 0 to be consistent with my notations. So it's 1 over square root n factorial. And what Slater determinant should you take? Psi I x j. Right? I forget about the omegas and all that. Where E1, En are the eigenvalues of H omega lambda, and phi 1, phi n are the eigenfunctions associated H omega lambda. To make things simple, let's assume that everybody in here in the spectrum is simple, right? So don't have a problem with choice. So you take this, and so how many should you take? Which eigenvalues and which? Well, you should take the n first eigenvalues, so epsilon 0 of n. So this is this ground state. Am I consistent with my own notations? Yeah, roughly I am. Forgot about the rho. This is just the sum from j equals 1 to n of the ej. Of course, these depend on lambda and omega, right? Of the ej, which you can also write as this thing. You can write as the integral of the energy, and you take the counting function omega lambda, right? So En omega lambda is the counting measure for H omega lambda. Well, up to where? Well, up to the energy En. And who defines? So let me assume, for the sake of definiteness, I assume now that the spectrum of my h omega starts at 0. So it contains the point 0, sorry, and it's contained in the half axis. Okay, just for the sake of definiteness, I assume that my free operator, single particle Hamiltonian, has a spectrum started at 0. So I start this integral at 0. Okay, and how is the energy En defined? Well, it is just the energy such that if you look at the counting measure, at En is just equal to n. But what is n? It's rho times lambda, right? So of course, if you do this, but you know that the counting measure has a limit, which is called the integrate density of states. So if you go to the limit, this thing tells you that where you should go, actually. So this is when lambda goes to infinity. I won't justify any of this, but this can all be justified, at least in some models. And, well, actually rather general models. This converges to the integral from 0 to e rho of e d n. And forgot one thing. Of course, there is here, you should write this, but this divided by lambda. Sorry, I forgot the 1 over n here. I forgot the 1 over n here. So I divide this by lambda, and I have a lambda here then. And I get that this is 1 over rho. Right? So I get that what I can estimate is that this En0 rho should go when n goes to infinity under the condition that the n is proportional to the volume with a constant rho. It should go over to e rho e dn divided by integral 0 e rho dn. Right? So e rho is just the Fermi energy. Okay. So, what do we learn from that? What do we learn from this computation? Well, there is good news and bad news. So, what we want to understand, so how to get to E, U, where did I put the n? Oops, some chalk. U, sorry, the U is here, the n rho. Right, well, unfortunately, we don't have much imagination. So the first thing we want to try is perturbation theory, right? So perturbation theory, but what is natural perturbation parameter? One thing we don't want to do is use the interactions as a perturbation parameter. That's something we want to avoid, right, as much as we can. So the natural perturbation parameter will actually be the density rho. Okay, so rho will be assumed to be positive, but we are going to take it small. Small independent of the size lambda, right? It's small but independent of the size lambda. So what's the idea? The idea is, of course, that you have few particles, so they should not interact very much. And as there are few interactions, this term, though as an operator it's pretty big, acting on the states you're interested in, it should be small. Okay, that's the basic idea. So, but you see one thing, nevertheless, you see that there is one problem. The problem is the following. If you fix rho even small, one thing that you need to know, even just to do this computation, you need to know high energies. Okay, one needs to know the spectral decomposition of h omega lambda up to energies, up to the Fermi energy. And this Fermi energy is macroscopic. So you need to know many states at the same time of your random operator. And that's not an easy task in general. If I take, for example, the Poisson model, which I'd like to be able to study, I don't know how to do this yet. Okay? So what we're going to do is we're going to take a simplified model. And this is why we introduced, oh yeah, well, I will make the remark now. Yeah, one thing, looking at this, just a remark about this localization, what I said, which is not obvious what localized means. Of course, even if each of these functions is going to be nicely localized, once you take the Slater determinant, they won't be localized at the same spot in space, right? Over your volume lambda, they live in different places in lambda. So if you take such a Slater determinant, this determinant will live inside the nth power of your cube more or less everywhere, right? It will live more or less everywhere. Of course, it will be quite dilute because you took the Fermi energy to be pretty small. but nevertheless, it will live more or less everywhere. So what is localization is not completely obvious. Okay. Now, I don't know how to make this rigorous for such a general model. So the other thing that I need, that I see from this formula, if I even want just to determine the Fermi energy with some precision, right? I also need to know the function n of e, the density of states. And usually mathematically what is known about n of e is actually, except for some special toy models, and this is why I'm going back to one such toy model, is, well, you is at best actually, if you take general models like the Poisson models, you have the fact that log n of e behaves like minus constant e to the minus t over 2, where the constant here can be computed. But such a precision, right, this is when e goes to the edge of the spectrum. But such a precision is not good enough for purposes of understanding the interacting fermions, right? You need to be much more precise than that. Sorry? D is a dimension. You see, I remember I started in particles in d-dimensional space, so take d equals 3. Actually, we're going to take d equals 1 very quickly.
All the particles?
No, E in this is just the energy of a single particle. That's for the one particle Hamiltonian. Okay? It's just to spot what are the difficulties. I mean, the mathematical difficulties you're going to encounter and where you should need actually to get the precise analysis of the objects that you have. Okay, so one of the difficulties is you need to know the density of states with a good precision. And as I said, in general, except for special models, this is why we're going to turn to special model, by the way, you don't know better than this. Okay, which is not enough. It doesn't provide enough information about what the Fermi, how the Fermi energy is coupled to the density of particles. So the model I'll be looking at, and this is not to speak about the spectral decomposition, that's a much cruder question, but still. We're going to look at a simple model. So this is the pieces model. So what's the pieces model? Well, I'm working d equals 1, so on R, and on L2 of an interval 0L, what I will consider my H omega, I replace lambda, the volume, by L, just by its length, right? It's just a single interval, will just by definition be given by the direct sum of H, of minus Laplacian with Dirichlet boundary condition on the interval ij. I'll tell you what ij is in the picture in a second. Where, so you take 0L, you throw Poisson points on the real axis. Okay, your sample omega throws Poisson points on the real axis. You keep the Poisson points that are inside 0L. This gives you a certain number of intervals. That I call ij omega. So here we have I1 omega, I2 omega. Let me put some dots here. Okay, and I minus 1 of omega, or n omega minus 1, sorry. Depends on omega as well. Okay, and what you do is you put Dirichlet barriers, Dirichlet boundary conditions, and you consider the direct sum of these operators. This is certainly localized, right? Obviously, the spectrum of this operator, because it's not sum, right? Commuting operators. Well, the spectrum of these operators is just the union of the spectra of my Dirichlet operators. So that's a good thing. Not only do I know very precisely what the spectrum is, but I also know very well what the eigenfunctions are, which is certainly going to play a role when I want to understand the perturbation theory from the free states. Okay? So the other nice thing is that, well, for this model, so do I need to show something else? Yeah, well, we have this. So, of course, let me just record this, but you all know this. So the energies of 8 omega L are just given by the pi k. So you have two indices. And here you have the length of Ej of omega. Oops, sorry. This squared, right, where k is larger than 1, and j runs between 1 and n omega. So this is a random number. Of course, yeah, the Poisson points, let me call these x1, x2, well actually, yeah, x1, x2, this is not 3, this is x n omega minus 2, x n omega minus 1. Yep, x0, that's fine. I got enough of them. And so the Poisson points, let's assume that the Poisson points have density mu, right? So they're uniform Poisson and the density mu of Poisson points. Okay. Okay. So typically this number, law of large number, this is L times mu, right? You have typically L mu times number with good probability. And so, well, essentially, if you look at the conditional probability of the length here, n omega being fixed, these are essentially given by IID random variables which follow an exponential law, right, up to some very small errors. Okay, so, and this enables you to compute the IDS. So first you define what we call the Fermi energy L of E, which by definition is just pi divided by square root of E. So this is just the smallest length at which you have an energy for the Dirichlet Hamiltonian, right, for an interval of this length at below energy E. And then you have that the density of states at E is actually equal to, it's not an asymptotic formula, it's an equality, E to the minus mu L E, mu 1 minus E to the minus mu L E. Right. Easy to compute. Again, it's a consequence of the law of large numbers. And what did I want to say? And of course, we can compute the Fermi energy at density rho for the free Hamiltonian. E rho is given by, well, pi mu divided by log rho squared. 1 plus little of 1. And you have the associated length, right, which is pi over E rho squared. So it's of order, log rho. Well, this can be computed more precisely, but we won't need it. Oops. Okay. Now, what did I want to say? So, of course, the number of levels. Maybe I start. Oh, here I have some board. Well, my board management is not the best. So, remark. If you look at the number of levels of the total Hamiltonian, meaning the direct sum, less than energy E rho, this is of course given by n of E rho L, right? But you can also, so this is, of course, n of E rho is rho, so this is rho L. But you can also look at the number of levels of this Hamiltonian that are not only between E rho, but between E rho and E rho 1 minus epsilon, right? And this is roughly of the same order. This is also rho L, meaning that the difference between the two, right? So it is equal to this, plus some little o, well actually, plus an O of rho to the power 1 plus delta times L, of course. So roughly, most of the levels, and this is due to the very fast decay of density of states, most of the levels, if you look at your random Hamiltonian for the levels below E rho, most of the levels are actually very close to E rho. Right? That's something which will play an important role in the future. Okay. Not all of them, but most of them. And, well, the first theorem. So let's now define, I didn't say anything about the interactions. Interactions. So when I take just to make it simple, u of x equals 1 over minus r0 of x. So r0 positive fixed. Okay, you fix some constant r0 positive. You could also look at delta interactions, but delta interactions in this case, because of the very special feature of this model is the fact that your eigenfunctions have compact support, right? Each of them, because it's easy with probability 1 to see that all the lengths here are rationally independent, right? This happens with probability 1. It means that all the eigenvalues are simple with probability 1, right? And so an eigenfunction lives in a single, for the single particle Hamiltonian, lives in a single of these intervals, right? So if you take something which has extension range 0 here, the only way you have interactions is when you put more than 2 particles inside one of these intervals, right? Otherwise, interaction just vanishes, okay? So this is why we took something which has some range, so that you really can have all the particles have a chance to interact with each other, okay? And the first theorem, well, I'm going to start over here again. The first theorem is the following. Theorem 1. So recall that, well, there exists some constant and some rho 0, such that for rho smaller than rho 0, you have that if you compare the density of the ground state energy per particle for the interacting Hamiltonian to the ground state energy per particle for the free Hamiltonian, well, then this is upper and lower bounded by rho times log rho to the minus 3 times some constant, and here you have rho times log rho to the minus 3. Recall that this, right, this you can compute, right, this is equal to E rho. Well, so it is roughly okay. So you see that the addition of energy, the supplement of energy coming from your repulsive interaction is actually exponentially small compared to the ground state energy, right? So you have to control some exponentially small terms, right? Rho is exponentially small compared to log rho, right? Actually square root. Okay, so that's the first thing. And of course, for the moment we only have this, we would like to get an asymptotic. I'd like to see what is the true constant that I have in front here. Okay, and this constant, well, will certainly depend on you. So, but I don't know what it is, and actually I don't even know what it exists. I mean, this still allows for some oscillations. So the second thing is about the ground state and about the autocorrelation function for the ground state. So that's theorem 2. So you pick some beta in 0, 1/2. Then again, there exists some rho 0 positive and some constant C positive, such that for any rho in 0, rho 0, if you pick B rho, a number which is larger than C log rho inverse, right? So when rho is small, this is getting large. For L and N sufficiently large such that N divided by L, this one should be close to rho. Again, sufficiently close to rho. I don't want to write the quantifiers. To rho with probability 1 minus e to the minus L to the beta. So with a rather good probability. If you take a vector y inside 0L to the n, and such that y has at least, oh, what did I say? N B rho components larger than L, little L rho, so this is the length associated to the Fermi energy times 1 plus 1 over c. Right? Then, if you look at the correlation function, psi 0 n, psi u, sorry, n x, psi u n x plus y dx, this is less than c e to the minus n b rho log rho. Right. So this decays. So it's not the exponential decay you'd expect in the length of the interval y. But nevertheless, what you see is that as soon as there are many components, right, of y that are over what could be considered in this picture the localization length, right, read the length of the support of your eigenfunctions, you see some very fast exponential decay kick in. Remember that in this model, without interactions, the eigenfunctions are localized in the sense that they have compact support. As I said before, most of them have compact support exactly of the size L rho here, right? This is the majority of the eigenfunctions below energy E rho have compact support of the size L rho. And what this is saying is that as soon as you take a vector, and if you take the ground state for the interacting fermions, shift it away by some vector that shifts sufficiently many components away, right, from this length, meaning that it doesn't allow these to overlap, then you see the exponential decay again. Okay? That's the way it shouldn't be interpreted. Okay. In a very strong way, meaning here put the modulus, so it's really the shape of the function, it's not the oscillation that makes this smaller. It's really the fact that the thing is living in two different places. Now, so that's the first statement about the ground state. Let me give a few more statements that illuminate what the ground state looks like. So, therefore, for this model, one can define the following thing. If you take an eigenfunction for the non-interacting case, non-interacting model, you can define an occupation number. So fix omega. So fix some realization of my Poisson points on the interval. You can define an occupation number. What is this? This is just the n tuple. So you have n omega intervals, right, in the Poisson, in the pieces model. Okay? And then what you can look at is how many, for this eigenfunction, we know that it's built by a Slater determinant. You can look at how many components of this Slater determinant fall into the first interval, how many fall into the second, how many fall into the third, and so on. Okay? So you have qi, q1, qn. So I write n, but n is n omega. It depends on omega, right? Okay. So you can define this.
In what space?
Sorry?
In what space is this interval? In real space?
Which interval? The interval here? It's in real space. That's just the following. Well, that's actually what I erased, or not?
No, okay.
No, it's here. It's just these intervals, the ij's, right? And you look at how many particles fall in here, how many in here, how many in here, and so on. Okay? And you define this as to be the occupation number. And a basic property of both the full and the, meaning the Hamiltonian with and without interaction, is that you can now define, let's define HQ to be the span of the eigenfunctions of psi, such that psi, q of psi is a given q. So q is an n tuple, right? To fix omega. So when omega is fixed, n is fixed, right? N depends on omega, but when omega is fixed, n is fixed. So fix omega, and you can take a number q is just an n tuple in n to the n omega, right? And look at this. And one of the nice properties of this Hamiltonian, right, which is due to the form of first the free Hamiltonian but also the interactions, in particular, but because they are by pairs, is that HQ for any Q are, sorry, what did I call it? H, N, U, omega invariant. And also H, N, 0, omega invariant subspaces. So you can decompose your Hamiltonian onto these subspaces. Yes, please. Oh, it's not a question. It's an announcement. Okay. Well, unfortunately, I won't have time to come to the title of my talk. Okay, 4 minutes. So maybe I can. Well, what you can. So the way to proceed to prove what I announced is there are 3 main things. First, you have to separate excited states from lower lying states. Well, I won't explain this, but this can be done. And one very useful thing for this is to use these HQs, right, to separate the excited states from the lower states. But maybe what is more interesting is the following. Then you have the following theorem. Once you have defined this, a theorem. One more. For beta in 0, 1/2, same thing as before. You can find a constant C positive, a rho 0 positive, such that for rho in 0, rho 0, if NL large, such that N over L close to rho, so it's such close, of course, to rho, close to rho, then with probability 1 minus e to the minus L beta, well, you can do the following. You can compare the occupation number. So you have this occupation number, so these are invariant. So let me just say 2 things. Because they are invariant, and what the other theorem, the other theorem I should put on the board, theorem, psi u n omega, omega almost surely is non-degenerate. Okay, this state, the ground state, is non-degenerate. This has an immediate consequence, is that it needs to fall into a single occupation subspace. Almost surely in omega, there is a q omega such that psi belongs to HQ omega. And now what you are going to do is to compare this q for the ground state psi u n omega with the one for the free ground state. And what do we use to compare this? Well, we use the 0 distance. What is the 0 distance? It's just the counting distance. So I have 2 vectors of the same length here, and I count the number of coordinates by which they differ. Distance 0 is just counting the number of coordinates by which they differ. So I count the number of intervals in which the ground state for the interacting Hamiltonian does not put as many states as the ground state of the free Hamiltonian. And what you get is that this number is both lower and upper bounded by a constant times n times rho, and by 1 over a constant times n times rho. Well, then I stop here. Thanks very much for your attention. Didn't have time to speak about the main, what I want to say at first, but okay.
Questions? Just a
Sure,
short remark. This model of pieces, it is described in our book.
Sure.
But not interaction. Just,
No. For of course, I don't pretend I invented the pieces model, right? What I'm saying, of course, you can find many information. There is a paper by Molchanov, Grenkova, and Sudaryev, 82 in communication and math physics, where they study the pieces model, and they study some exactly solvable model, right, associated to it. And well, maybe if I have just 1 more minute to say something. Of course, what you'd like to do is to do the same thing for a real model, meaning not the pieces model, but take Poisson points on the real line, put bumps at these Poisson points, and do the same thing. Okay? So part of it can be done, meaning I know how to analyze the density of states up to the precision that is known, that is needed to do this, right? Meaning that I can give complete asymptotics for the density of states. What I don't know how to do, I also know how to and it's not very difficult because it proceeds from the same analysis as the one for density of states. I know how to describe that the states for the Poisson model need to be superpositions of states that are essentially living in these intervals, except that they leak out a little bit. I can control the leakage, right? But I don't know yet how out of these individual states construct the true states of the random Hamiltonian with the tunneling effect. Right? That's the difficulty that I face now. Okay, how to reconstruct once you have individual states living in here, how do you reconstruct the true states for the Hamiltonian? Because then you have to control the tunneling. There is no tunneling here. This is what simplifies things a lot. No tunneling. Tunneling has been suppressed. But in the true model, you'll have tunneling. And so states for just this interval and neighborhood of this interval will not give you states for the globe, for the total Hamiltonian over the whole 0L interval. Right? You need to control tunneling.
Anyway, to connect it, there are papers by Altschuler and Delainer and other co-workers
Yes.
On the localization problem of many bodies. Is there a way to connect this to what they are doing?
But the problem is my understanding of these papers is so scarce, right, and so lacunary, not to say void, that actually I have a hard time understanding what the statements are and what model they're looking at. So,
I ask a simpler thing. Your interaction is a two-body interaction.
Yeah.
And so somehow I was expecting to see somewhere that the interaction energy, this is the interaction energy.
Yeah.
There must be some regime where it is quadratic in the density. Just Hartree-Fock. Why I don't see any.
But Hartree-Fock is a mean field model, right? So here there is no mean field. I mean, this is quite different.
Yeah, but in perturbation theory,
I mean,
with mean field approximation.
With
you have a
bosons.
two-body operator, and you're taking in perturbation theory, you're taking this expectation value in the free ground state.
Yes, but if you take the expectation value in the free ground state, it's exactly this. Per particle, the expectation in the free ground state can be computed, and it's asymptotic to this when rho goes to 0.
Expansion, Martin. Viral expansion, we have pair interaction, but rho.
I divide, sure, there is one rho less because I divide by n, not by the volume. That's correct.
That's a stupid question. Okay.
Not by the volume. I divide, oh yeah, this is, you were looking for a rho square. Okay, I see. No, this is the n because you take per particle. Okay. If I take per unit of volume, there is one rho more. Definitely.
Okay. With this clarified, maybe we can, one more, this is the final one.
Yeah, in your theorem too, did I get that correctly, that you do not expect any further decay in y, in the size of make y very big, because as soon as the components of y are bigger than your length L rho, then eigenfunctions are...
The further decay is controlled by this number, right? I didn't put it in y. It's controlled by, this number can be anything that is larger than that.
Yeah.
So it is controlled in some way by this number.
But now, I mean, you don't say, you don't specify how big the components are that are bigger than C log rho.
No, that's true. That's true.
Do you expect this correlation to get?
No.
No. Okay.
No, actually not, because if you think of what the free ground state look like, it lives right in here in many intervals. Yeah. That are roughly away from each other by something which is of order 1 over rho, right? And so at some point, even if you shift one of them, you're going to hit the one that is living far away, right? So you don't expect much more than this. There may be some intermediate regime because here I control from L of rho. Remember, L of rho is log rho, right? It's log rho. So there is something between log rho and 1 of rho. You may expect maybe that there is something much smaller.
All right, let's thank all the speakers and as well as
Thanks very much.